You're able to see my screen?
Yes, sir.
Okay. So if I remember correctly, I think we have solved this problem in the last class, right? We have solved this problem in the last class?
Yes, sir.
Yes,
We have
sir.
solved it. Yes.
Yeah, and we have not done the maximum shear stress theory, or did we do maximum shear stress theory also?
No, sir. I think that was the pending thing.
Okay. All right. So until now, what we have looked at was distortion energy theory, which is very good for ductile materials. Correct. And now let us look at the next failure theory, which is called a maximum shear stress theory. Okay, so this was first proposed by Coulomb, and later this is uh, improved in its description by Tresca and Guest, and hence it is called, the current version that we are using for the ductile materials is called Tresca-Guest theory. In the beginning with Coulomb, it was mostly on soils. They used the shear stress theory, but for the metals, ductile materials, the description was mostly formulated by Tresca and Guest, and hence it is called Tresca-Guest theory. And that is the version that we are using now. So what does this series says? It says the following: failure, that means in this case, when we say failure, it is the onset of plastic deformation, right? So this happens when you're applying a three-dimensional state of loading in a component. At each and every point, you will have some shear stress, right? And for example, if you look at this particular Mohr circle, you can see that if you are doing a uniaxial tension test, and let us say sigma y is your yield strength of the material, right? And if you apply your sigma 1 becomes yield strength, that is when the failure happens. But we have seen that if you draw this Mohr circle, each and every point on the Mohr circle represents the state of stress at a plane which is oriented at an angle theta from the axis about which the normal stress is applied. That's what we have discussed. So if you look at this particular point at which the shear stress is maximum, for a case of uniaxial tension, this maximum shear stress will be, if you are loading up to the yield strength of the material, then the maximum shear stress will be sigma y by 2. That is when the onset of plastic deformation takes place. That means this we can refer to as something called shear yield strength of the material. So when the shear yield strength of the material, which is sigma y by 2, 0.5 times sigma, that is the bounding value. And now if you draw the stress strain diagram, and if you draw the Mohr circle for your state of stress, and let us say that Mohr circle you have applied up to here, then the Mohr circle will become something like that, and the maximum shear stress will be somewhere here, which is less than sigma y by 2, and hence it will not fail. But when the maximum shear stress reaches the sigma y by 2, that is when failure happens. So that failure occurs when the maximum shear stress in a part exceeds the shear stress in a tensile specimen at yield point. So you actually look at the maximum shear stress tau max in your Mohr circle, and any tau max becomes sigma y by 2. That is when yielding occurs. Otherwise, the material is safe. Is this clear to all of you?
Yes, sir.
Is there any question there?
Yes, sir.
So if you have any, so those of you who are silent, I am assuming that it is clear to you. If it is not, please raise your hand. We will try to describe it a little bit more detail, but I think it is probably clear to you. So now the question is, how do we do it when you have a three-dimensional state of loading? If you have a 3D state of loading, we have discussed how to draw Mohr circle. Let us say if you have a 3D state of loading, we have three principal stresses, sigma 1, sigma 2, and sigma 3. And on the sigma plane, you identify sigma 1, sigma 2, sigma 3. And we have discussed that the convention is sigma 1 is greater than or equal to sigma 2 is greater than or equal to sigma 3. That is our usual convention. So when sigma 1 is greater than sigma 2 is sigma 3, you identify these points, then draw circles between sigma 1 and sigma 2, sigma 2 and sigma 3, and sigma 1 and sigma 2. The area outside these two small circles and inside this large circle is the area in which you will have valid state of stress, right? And they, unlike a uniaxial, unlike a 2D state of stress, identifying the stress on a particular plane will become a little bit more complicated here, but I am not going into the details of that. But you can clearly see when you look at this Mohr circle, the maximum shear stress will be equal to sigma 1, that is maximum principal stress, minus minimum principal stress divided by 2. Sigma 1 minus sigma 3 by 2. Instead of just remembering it as sigma 1 minus sigma 3 by 2, you just consider this as a maximum principal stress minus minimum principal stress by 2. The moment you have that, then what is our maximum shear stress theory telling us? The maximum shear stress theory tells you when the maximum shear stress in the material becomes equal to shear yield strength of the material. This is the maximum shear stress. Then that becomes equal to shear yield strength. Shear yield strength is sigma y by 2. Then the failure occurs. That means sigma 1 minus sigma 3 is equal to sigma y. Is failure or greater than or also greater than or equal to sigma y is what we call failure. Okay, so this is the condition for failure for maximum shear stress theory. Is this clear? Or
Yes, sir.
so now let us try to draw the failure surface. Now this is the case for a three-dimensional state of stress where sigma 1 is greater than sigma 2 is equal to greater than sigma 3. So sigma 1 and sigma 3 are maximum and minimum principal stresses. Now I would like to draw the failure surface in 2D. That means for the case of a plane stress problem. When we say plane stress problem, one of the stresses is 0. Either sigma 2 is 0 or sigma 3 is 0 or sigma 1 is 0. Okay. Now let us take the case of sigma 1 is greater than sigma 3 and sigma 2 is 0. Right? Because that is your principal, one of the stresses. So now if you look at carefully, from the three-dimensional perspective, sigma 1 is the largest stress, 0 is the smallest stress. So if you plug into this equation, sigma 1 minus 0 greater than or equal to sigma y, or sigma 1 minus 0 is equal to sigma y. Correct? That means sigma 1 is equal to sigma y is your failure surface. For the case 1, sigma 1 is equal to sigma y means that straight line is your failure surface first. Is that clear or not? So maybe I will describe that in more detail. Let me share my screen. Share advanced. Oh, I think we have done maximum shear stress theory up to here. So we have done it in the last class. So our today's date is 27th October. So the statement of maximum shear stress theory is sigma 1 minus sigma 3 is equal to sigma y. Because what we are saying is when the maximum shear stress becomes equal to shear yield strength of the material, that is nothing but 1/2 of the normal yield strength of the material. Right? That is what, and when you have a stress state like that, sigma 1 is largest, sigma 2 is intermediate, sigma 3 is smallest, then the maximum shear stress will be sigma 1 minus sigma 3 by 2, and sigma 1 minus sigma 3 by 2 equals sigma y by 2, and then this is your maximum shear stress. So now in 2D, how do we plot the surface, right? So let me draw first the axis of sigma 1 and sigma 3. This is my sigma 1, that is my sigma 3. Now I am considering case 1 is the following. There are several scenarios that are possible. Let us say both sigma 1 is greater than sigma 3 is greater than 0. Because we are talking about plane stress, one of the stresses have to become 0. One of the principal stresses have to become 0. So let us say I am calling sigma 2 is the minimum principal stress. Now, according to maximum shear stress theory, what we said, maximum principal stress minus minimum principal stress. So here in this case, because sigma 3 is greater than 0, so the maximum will be sigma 1 minus minimum will be 0, that is equal to sigma y. That implies sigma 1 is equal to sigma y is your boundary, failure boundary. Let us say that is my sigma y. Right? So I can draw, that is my failure line. This goes infinity. Right? Now, let us look at the case 2. What is case 2? Sigma 1 is greater than 0, but 0 is greater than sigma 3. That means in this case also sigma 2 is 0, but sigma 3 is negative. Sigma 1 is positive, sigma 3 is negative. Right? In that case, your maximum principal stress minus minimum principal stress is equal to sigma y. That will be your failure surface. So what is sigma 1 minus sigma 3 is equal to sigma y? Because if you identify 4, 1, 2, 3, 4. So this will be my sigma y, correct? This point is my sigma y. Now, the line should be sigma 1 minus sigma 3 is equal to sigma y. That will be this line.
Sir, one small doubt.
Yes.
When you say that sigma 1 is greater than 0 and sigma 3 is less than 0, if you add, the yield strength should be positive, right? Because sigma 1 minus sigma 3. So
yeah, sigma 3 is negative. So minus of minus becomes plus, no?
yeah, but then the yield strength cannot be at the negative axis, right? It should be on the positive axis.
No, it is sigma y is yield strength is magnitude. You are only talking about magnitude, isn't it?
Yes.
Yeah. So that is the equation sigma 1 minus sigma 3 is equal to sigma y will be that. Whenever your sigma 1 is equal to 0, let us say sigma 1 equal to 0. That is on this line, correct? 0 minus sigma 3 is equal to sigma y.
Yes.
That is what this line is, correct? That is minus sigma y, no?
Yeah, by equation, yes. I was
Yeah.
only thinking
So
of the
understanding is that here one assumption is that the material will have same yield strength in both tension and compression. So sigma y
got it. Yeah.
in tension is equal to sigma y in compression. That is the assumption that we. Okay. So this is case 1. For case 2, that is the thing. Now let us go to case 3. Case 3 is 0 greater than sigma 1 greater than sigma 3. That means both sigma 1 and sigma 3 are negative. Both are compressive in nature. Then what is the maximum principal stress? 0. Minimum principal stress will be sigma 3 is equal to sigma y. That implies sigma 3 is equal to minus sigma y. Agreed? So I will identify this is my minus sigma y. Do you agree?
What is the difference between case 2 and case 3, sir?
Case 2 is one of the principal stress is positive, another principal stress is negative.
Oh, okay.
And case 3, both the principal stresses are negative.
Got it, sir. Thanks.
Yeah. So then sigma 3 is equal to minus sigma y. Where is the line? How does the line look like? Sigma 3 is equal to minus sigma y. So the line should look that is my line, right? This is equal to sigma 3. That is case 3. Right? So the bounding area of all three of them is where? This is case 2, case 1, case 3. Right? So let us, this is the scenario where sigma 1 is greater than sigma 2 is greater than sigma 3. And similarly, if you take sigma 3 to be the positive. So for example, what we have done is sigma 1 greater than sigma 3 greater than 0. Similarly, you can say sigma 3 greater than sigma 1 greater than 0. Let us say sigma 3 is the largest principal stress. Then you will have your boundaries. I am drawing the boundaries again. That is another sigma y. And if you would draw, that is one line. That is another line. This is another. So now your surface will be this is case 3, case 2, case 1. Similarly, if you reverse sigma 1 and sigma 3, sigma 3 being the largest principal stress, then this and this will come in. So this total area enclosed by this is your locus for failure surface in 2D, or it is called failure locus. And what is this? What is the shape? What is this shape? How many sides are there?
Hexagon.
It's a hexagon in 2D. Okay. So the failure locus or yield locus. Failure here is nothing but yield locus for maximum shear stress theory in principal stress space is a hexagon. For distortion energy theory is an ellipse, which we have seen in the last class, or this is also called von Mises theory. Is that clear?
Yes, sir.
Yeah. So the failure surface for the maximum shear stress theory in 3D will also be a cylinder, but instead of a circular cylinder, it will become a hexagonal cylinder. That is the only difference. Otherwise, it is very similar to maximum shear stress theory. Otherwise, distortion energy theory. Now,
Sir,
yeah,
sir,
please.
can you go to the, can you slightly go up, sir,
Yes.
to the graph?
Hmm.
Sir, here, can you just, if it is okay, can you just explain again that sigma yt is equal to sigma y equal to c, that line?
Which one? Case 1 or case 2 or case 3 or all three?
We had drawn 3 lines, case 1, case 2, case 3 line, and then we have extended on the other side, right?
Okay. So now imagine a case Now let us do a case for sigma 3 greater than sigma 1 greater than 0. Okay. Then according to maximum maximum shear stress theory, what should be the equation? Sigma 3 is the
Sigma 3
maximum
minus
principal
0.
stress minus 0 must be equal to sigma y. That implies sigma 3 is equal to sigma y. So sigma 3 is equal to sigma y is which line? This is your sigma 3 is equal to sigma y line, isn't it?
Yeah.
That is how I got this line.
Got it, sir.
Similarly,
Fine.
yeah, now
Same
similarly,
interpolated.
this one is, so I will write down what do I mean by that. This is sigma 3 is equal to sigma y line. This is sigma 3 minus sigma 1 is equal to sigma y. Instead of taking sigma 1 greater, you take sigma 3 to be the largest principal stress. That's the only difference.
Got it, sir. Got it. Thank you, sir.
Yeah. So now let us try to carefully draw the failure surfaces for different failure theories. Okay. So let us say this is sigma 1, that is sigma 3, and let us identify sigma y. 3 units, 1, 2, 3 units, 1, 2, 3 units, 1, 2, 3 units. Okay, that is my sigma y's. Let us talk about maximum normal stress theory. What does it say, tell us? What does maximum normal stress theory tell you?
Sigma y equal to sigma 1.
When the maximum principal stress is equal to yield strength of the material. Right? Now, if you take sigma 1 greater than sigma 3 greater than 0, correct? Then the entire loading is tensile load, and hence sigma 1 is equal to sigma y is your failure line.
Fair
Do you agree?
criteria.
I can draw the entire line, that's okay. Similarly, when sigma 3 is greater than 0, sigma 3 is equal to sigma y. Sigma 3 is, let us say sigma 3 is greater than sigma 1 greater than 0, then sigma 3 is equal to sigma y as our failure line. So I can draw this line. Agreed? Okay.
Yes, sir.
Now, the same thing will happen in compression also, isn't it? If you do in compression, we also have a compressive yield strength, which is also same as tensile yield strength. Then if you have sigma 3 is equal to minus sigma y, minus sigma 3 is equal to minus sigma y, that is when failure happens. Minus sigma 1 is equal to minus sigma y, that also when failure happens. Minus sigma 1 is equal to minus sigma y, which is the line?
Negative y-axis, horizontal.
That is minus sigma 1, right?
Oh.
And sigma 3 will give you this line. So the area enclosed by these 4 lines is our failure surface, isn't it? So what would that by failure surface be? That one, that one, that one, that one, isn't it? That is so I would call this as maximum normal stress theory, MNS. That is the failure surface for maximum normal stress theory. Now let us draw for maximum shear stress theory in green color. How does it look like? In green color, we have just now drawn. That is your maximum shear stress theory, isn't it?
Yeah.
Now
Yes, sir.
you have to draw in red color distortion energy theory. How does distortion energy theory look like? You have to draw an ellipse. Isn't it? That is your distortion energy theory. This is what we have seen earlier, isn't it?
Yes.
Yes, sir.
Oriented at an angle 45 degrees. Now, let us try to understand this little bit carefully. Okay. Let us say you are applying load on a material, on a component, a three-dimensional state of loading, wherein sigma 1, let us say sigma y is equal to 400. This is 400, 400, 400. Your state of stress sigma 1 comma sigma 3 is equal to 200 comma 200. Both are equal. So let us say 300, not 400, 300, because that's easy for me to draw. Okay. So now sigma 1 is equal to 200, sigma 2 is 3 is equal to 200. That is the data point. Okay. So suppose if you have a state of loading, something you are doing like that, sigma 1 is 200, sigma 3 is 200. Equibiaxial loading. If you plot that in this sigma 1, sigma 3 plane, that is the data, that is the point loading scenario for your specimen. Is this safe or unsafe?
Safe.
It is safe, right? Now, let us carefully observe this fellow. According to, now let us calculate the factor of safety. According to normal stress theory, according to shear stress theory, according to distortion energy theory. What is factor of safety?
Yield strength divided by applied load.
Yield strength divided by normal stress theory, sigma P max, maximum principal stress. Isn't it? Here, yield strength, shear yield strength divided by maximum shear stress. Distortion energy theory, yield strength by equivalent stress. That is what our definition of factors of safety, isn't it? For shear stress, shear yield strength by maximum shear stress. For distortion energy theory, yield strength by equivalent stress. That is how you define, isn't it? Are there any questions there? There are no questions. Now, according to normal stress theory, what is the yield strength of the material? 300. What is the maximum principal stress? 200.
200.
So 1.5. That is the factor of safety. What is the shear yield strength? 150. Correct? Because yield strength by 2, sigma ys is equal to sigma y by 2. What is tau max?
0.
Is it
Because
0?
sigma.
It's a, what is sigma 2?
So it's sigma y by
0.
2.
Sigma 2 is 0. That will be tau max will be 200
200.
minus 0 by 2. That is
Oh.
100. Isn't it? 1.5. And how about distortion energy theory? Sigma y is 300. We have to find equivalent stress. What is sigma EQ? We have, do you remember the formula?
Square root of
Square root of 3
sigma 1.
Square root of sigma 1 square plus sigma 2 square plus sigma 3 square minus sigma 1
Minus
sigma 2 minus sigma 2 sigma 3 minus sigma 1
minus
sigma 2.
sigma 1 sigma 3.
So square root of sigma 1 is 200 square, sigma 2 is 0, sigma 3 is 200 square, minus 0, minus 0, minus 200 square. Yes or no? Yeah? Because sigma 2 is 0, no? So this is 0, this is 0. So this plus 200 square minus 200 square goes away. Root 200 square, that will be 200. So sigma equivalent will be what? 200.
200.
That is 1.5. What you have observed?
Factor of safety is same.
Same. Now let us take a scenario where the loading is 200 comma 100. Sigma 1 is 200, sigma 3 is 100. So what will be the factor of safety according to normal stress theory?
Should be 1.5.
Should be 1.5 because that is still 300 by maximum shear stress is 200 still. That is 1.5. How about shear stress theory? Shear yield
Same.
strength is 150. Again, the minimum principal stress is 0. So then this will be 100. That will be still be 1.5. How about this? Sigma y is 300. Equivalent stress we have to calculate, isn't it? So what will that be? Equivalent stress, let us calculate. Square root of 200 square plus 0 square plus 100 square minus 0 minus 0 minus 200 into 100. Isn't it? So what would that be? That will be square root of 200 square plus 100 square minus 200 into 100 will be how much? 20,000. Isn't it? All right. So that will be how much? 200 square is how much?
173.205.
173.2. So it is not 200. Now it is 173.2. So what is the factor of safety?
One 1.732 is what I'm getting.
So you are getting higher factor of safety. 1.73 or whatever. You are getting higher factor of safety. Now let us try to understand this. So depending on the state of stress, your factor of safety for different failure theories is changing. That actually can be nicely understood by this graph. So how do you calculate the factor of safety from the graph? If you, this is your 200 by 200, 200 come 100 is this fellow, isn't it?
Excuse me, sir, but I think the screen is stuck actually. I cannot.
Oh, is it?
Yeah, I
Yeah,
think even
graph is half visible. Yeah.
I mean, it's not moving. Yeah, now your pointer.
Now it is moving.
Your pointer came. But
Oh, I think let me stop and reshare. Yeah. Now it is 1.73. Oh, all these things did not come earlier.
no,
Oh, okay.
but we followed it.
You followed. Okay. So this is 200 comma 200. This is 200 comma 100. Now, how do we calculate graphically the factor of safety? You just draw one line through the point up to the boundary of the failure surface. And for the case of 200 by 200, all the three failure theories are meeting at that point. Can you see that? This is the point at which all three failure surfaces are meeting. Maximum shear stress theory, normal stress theory, and distortion energy theory. So let us say this is O, and that is P, that is Q. Then your factor of safety, N, for any specific failure theory is OP by OQ. What basically it is telling you is that in order to get failed, you have to go up to point P, but you are only at Q. The ratio of OP by OQ is your factor of safety. Because on this line, the failure point for normal stress theory, shear stress theory, as well as distortion energy theory is happening to be the same point. All three failure surfaces are at the they are intersecting with each other. That is why you got the factor of safety to be same. Now look at this fellow, the other guy. 200, 100. So now for this fellow, O is the same. This is Q is the same. This is P1 and P2. And if you carefully observe, if you have to write the factor of safety, factor of safety for distortion energy theory should be written as what? OP2 divided by OQ. Because distortion energy theory line is up to here. Interestingly, in the first quadrant, maximum shear stress theory and normal stress theory coincide. Their surfaces are one and the same. And hence, normal stress theory is equal to shear stress theory, that is equal to OP1 by OQ. And you know OP2 length is larger than OP1 length, and hence distortion energy theory will give you a higher factor of safety compared to maximum shear stress. So your maximum shear stress theory always, if you look at the entire diagram, everywhere the distortion energy theory factor of safety will be either equal to shear stress theory or more than the shear stress theory. It will never be less than the maximum shear stress theory. Can you see that? Suppose if I am looking at this particular fellow, let us say the stress state is here, then the way that I need to draw the line, this is my stress state, then I need to draw the line like that. Now, sorry, I have not completed the line properly. So this is my Q. Now if you carefully observe, this is my P1, P2 and P3. So what is the factor of safety for normal stress theory?
OP1 by OQ.
OQ. What is the factor of safety for shear stress theory?
OP3 by OQ.
And distortion energy theory will be OP2 by OQ. Correct? So depending upon how your stress state is, the factors of safety for all three theories can be different. And you will see that the maximum normal stress theory does not match with the experimental data. And hence, it is not a good theory to be used for ductile materials. Whereas, for shear stress theory and distortion energy theory match with the experimental data reasonably well. And hence, they are better theories to be used. However, between distortion energy theory and shear stress theory, you see that shear stress theory is always more conservative. That means it assumes less factor of safety for the same state of stress, and hence shear stress theory is more conservative compared to normal distortion energy theory. Can you see that?
Yes, sir.
Okay. So any questions here?
Sir, then I can design my part based on maximum shear stress.
If you design your part based on shear stress theory, it will be more safe, but that is going to increase the weight of your component, isn't it?
Yeah.
And in the literature, it is seen that the data is going to match mostly with the distortion energy theory. So I think if you don't want, if you are okay, if the part is extremely critical and you don't want to take any risk, then you might want to use my shear stress theory. But otherwise, it is better to use distortion energy theory so that you can reduce. If you are very confident on the calculation of your stresses in the body, right? Then you probably want to use distortion energy theory in order to reduce the weight of the component because it is less conservative. Is that clear?
Yes.
Any other questions? So if there are no further questions, now I will give you a problem. Let us try to solve this problem. So I am giving you state of stress for a component whose yield strength is in tension, yield strength in compression is 100 kilopounds per square inch. Now, you need to estimate the factor of safety for the following states of stress: 70, 70, 0, 30, 70, 0, 0, 70, minus 30, 0, minus 30, minus 70, 30, 30, 30. Using the factor of safety I wanted, this is case A, case B, case C, case D, case E, and here this is maximum normal stress theory, maximum shear stress theory, distortion energy theory. I wanted you to fill in the factors of safety in this table. Can you get started? For these states of stress, I want you to calculate the factor of safety. Once I give you 10 minutes to fill in this table. Okay. So I will ask randomly someone. I will not ask what is the answer. I will ask the name. So I would expect everyone to start. In the meantime, if you have a question, please ask. Was there a question?
No, sir.
Answer only we are trying to.
No. Sorry. You please continue. I will ask one by one.
Okay, sir.
Okay, sir.
Are you done or you are doing?
We are doing, sir. We are doing.
Okay. Go ahead. Yeah. Once you are done, you tell me that we are done, then I will ask. I'll give some
2,
time
3
for people. Yeah.
Sir, 2-3 minutes, sir. Allow me 2-3
Yeah,
minutes.
take your time. Yeah. So can we now discuss the result?
Yes, sir.
Okay. So I'll ask Vijay Raj. Vijay you are not there. Satish Kumar.
Yes, sir.
Yeah. So you got the results for the first 70-70-0.
Yes, sir. It's 1.43.
Which one? Which theory?
It's MNS is 1.3, sir.
1.4.
Point?
Sorry, 1.43, sir.
1.43, sir.
All of them are 1.43?
Yeah.
Yes, sir. All of them 1.43 only, sir.
Okay. Then all are safe. That means this guy will not fail.
Yes.
Next. 30-70-0.
Sir, 1.43, 1.43, 1.64, sir.
1.64 for one basis, huh?
One
Yes.
versus.
One.
And this is 1.43, yeah?
Yes.
Okay. C.
1.43.
Which one? Normal stress theory is
1.43. Shear stress is 1 and 1 versus is 1.12.
1.43. Shear stress is 1. 1.12.
1.2.
Sir.
1.2. So that means, according to shear stress theory, it is failing.
Yes, sir. It's going. Yes, sir.
Yes, sir.
Rahul, can you tell me about stress state D? Rahul B. Sharath?
Sir, stress state D is 1.43 for
Okay.
MNS.
MSS
1.43. And for distortion energy, I'm getting 1.64, sir.
So it will be same as B, isn't it? Because it's just the change of sign, that's all.
Yeah.
About E. What is E?
For me only, sir, or?
Yeah.
Okay. I'm getting 3.33. Yeah.
Shear stress?
Shear stress, like, I'm not sure, sir, whether I'm getting wrong. I'm not.
What are you getting?
It looks like infinity.
Infinity. And?
Yeah, same infinity.
Why do you think it is wrong?
It is not wrong, sir. I'm getting also same thing actually. Infinity.
Everyone
only.
is getting. Is there anyone who got something else?
Got infinity only, sir.
Everyone is getting infinity.
Yeah.
What is wrong then?
There is nothing wrong, sir, because 30 and 30 and 30. So for CS is max.
There is no
30 minus
deviate or a
30 will be,
component.
yeah.
It is the hydrostatic loading. We have discussed
Exactly,
that, right?
Exactly.
When you have hydrostatic loading, there will only be volume change, but shape will not change. If there is no shape change, there is no distortion. That means there is no plastic deformation.
Okay.
That is why these two theories are predicting it correctly, but the normal stress theory is saying that it will fail. So that is why normal stress theory is a dangerous theory to be used.
And even with the formula, if I go, sir, like sigma max of sigma 1 minus sigma 2, or max of sigma 2 minus sigma 3, or like that. So because all the stress are similar, so like the something minus something is 0 only, so it's going to be 0 only in that.
Yeah. So it is, the formula is obtained from the theory, right? So it should match. The concept and the formula should make sense, right?
Sure. Yeah. Right.
Okay, good. So we are able to, given a three-dimensional state of stress, now we are able to compute what happens. So now let me give you another problem, because you need to get. Yes.
I have one doubt. For shear stress theory, tau max is equal to sigma y divided by 2, right? So in that case, do we need to
No.
I mean, the numerator is 50 instead
Yeah,
of
it's
on.
whatever may be the numerator, the denominator being 0 will make it infinite, right?
Okay.
The denominator is what?
Denominator is
Here
infinity.
yield
0.
strength by maximum shear stress. No matter what the numerator is, the denominator is 0. That is why it becomes infinity. Got it?
Okay. Yeah.
So your N for maximum shear stress theory is sigma ys by tau max. Sigma ys is 0.5 times sigma y. Tau max is sigma 1 minus sigma 3 by 2. Right? Which is sigma 1 minus sigma 3 times 0.5. 0.5 gets cancelled. That is equal to sigma y by sigma 1 minus sigma 3. Sigma 1 minus sigma 3 is 0. Sigma y by 0 is infinity.
Makes sense. Sorry.
Yeah. So let me give you another problem. Yeah. This is more realistic problem. Try to read and work out. I will not extend any help now, but I would like you to try.
So can you just zoom out a bit, sir, because the full screen is not visible. Zoom out a bit, sir. Sorry.
It is full screen, no?
Yeah. Got it. It was my fault. Sorry.
So here what we have is a propeller drive shaft of a aircraft. So wherein you rotate this propeller and then there will be a torque applied on this. So that torque is 40 Newton meter. And the propeller thrust, because of the thrust, there will be an axial force on this fellow. That means it is a combined stress problem.
Yeah.
Because of the 400 newtons force, you will generate axial stress, that is normal stress. Because of the torque, you will generate shear stress, right? So you have a combined stress state, and now what? This is a hollow shaft. The shaft is to be 20 mm in diameter. In the service, the shaft will be subjected to a driving torque of this, and you need to find out what is the wall thickness. Where here, in the case of polar momentum of inertia, this R will be 10 mm in diameter, and we need to find out what is this thickness for this guy to not fail. Here, the factor of safety, assume it to be 1, what it will be. If the factor of safety is assumed to be 2, what should be the thickness, and so on, we can find out. Is the question clear to all of you?
Yes, sir. Yes, sir.
Sir, can I ask for your help if you allow,
Yes.
please? So you have taught us regarding that principal stress and maximum shear stress for the plane problem, right? So there is a formula sigma 1, sigma 2 is equal to
No,
sigma
no,
x
no.
plus
But
sigma y.
previously we have seen sigma 1, sigma 2, sigma 3. It is not a plane problem anymore.
All right.
It is a three-dimensional problem. Even in the case of three-dimensional problem, the maximum shear stress is what matters in the case of shear yield strength. And in the case of distortion energy, equivalent stress is what matters.
Okay,
So
sir. Noted.
you need to find out what are the principal stresses, sigma 1, sigma 2, sigma 3, and
Difference of that and then divide by 2
difference
and
of the
then equate.
maximum and minimum principal stress will be my maximum shear stress.
Fine, fine. Noted, sir. Thank you. Well, sir, this sigma equivalent which we are going to calculate, can we use the formula sigma x minus sigma
Yeah, you can use.
by whole
Either
square
way, it's
divide?
fine. Yes. You can use that also.
And then what I'll get, okay, let me try. Okay, fine.
Okay, any progress? So I'm hoping that this is how you are doing. So you know that the normal stress is load by area. When you are calculating area, that area should be the hollow section area. That will be 2 pi r times T. So that will be minus 20 by pi T, because T becomes a variable here that we need to evaluate. Are you doing that way? And should note that this is a compressive state of stress and you have to have negative sign there. That is very important. And tau shear stress is TR by J, because the torque applied is 40 Newton meter. Radius is 10 meters. And J, you have pi r cube by 2 pi r cube T. So all that you plug in, then that becomes 200 by pi T. And 20 by pi T is sigma. So tau can also be written as minus 10 sigma, whatever. And then your principal stress will become this. You can calculate, simplify that, and it will become an equation in terms of T. And our maximum shear stress theory says that sigma 1 minus sigma 3 is equal to sigma y. Or you can also use equivalent stress formula, because we are talking about maximum shear stress theory. We are required to find out tau max. You can also find out using the formula tau max if you have. Otherwise, sigma 1, sigma 3 you will find out. And by plugging into the previous equation, you will get sigma 1 to be this and sigma 3 to be that. And according to maximum shear stress theory, sigma 1 minus sigma 3 should be less than or equal to sigma y, assuming factor of safety is 1. Right? If your factor of safety is some number, then you have to accordingly modify this formula. Is equal to is sufficient. And then when you work with it and you see that your thickness should be greater than or equal to 0.319 millimeters. If you increase factor of safety, then this number will increase accordingly. So this is what we were asked to show. Show that the thickness should be at least 0.319 meters mm, and that is what is shown here. Is that clear? The procedure?
The
Professor,
Yes,
just one
calculation.
one thing, sir. This can you go to that sigma p? Sorry, I'm sorry, sir.
Mhm.
Sigma p. So minus sigma by 2 plus minus this under root 100.25 and modulus of sigma. I'm sorry to ask this, sir, but a bit elaboration on this, please.
No, sigma p. There is a one can actually find the equation for principal stress using normal stress in all the directions and shear stresses. Okay.
Yes.
If you
Yes, sir.
plug in that formula, this is what you will get.
Okay.
Okay. And there are two, because it's a two-dimensional thing. So there are only two principal stresses, right?
Right, sir.
The
Definitely.
loading is two-dimensional because there is only axial stress in this direction and shear stress. So you can simplify that as a 2D problem. It is not a 3D problem. Although the problem itself is 3D, but it can be simplified to 2D because the state of stress is only 2D. Can you see that?
Yeah. Right, sir.
And once you have the principal stresses, you can now calculate the using maximum shear stress theory. Now you can also do that using distortion energy theory if you wish. By knowing the principal stresses or using the sigma and tau, you can calculate the equivalent stress, which will again be in terms of T, and then you need to solve that equation. And once you solve that equation, and you will get the value of T. So you can also do that. What should be the thickness for it to be safe with a factor of safety of 1? Now I would like you to do as a homework problem, instead of factor of safety 1, if I change the factor of safety to be 2 or 3, what should be the value of this according to maximum shear stress theory and according to principal distortion energy theory? Okay, is that clear?
Yes, sir.
Clear, sir.
Sir,
Yeah.
I'm finding bit difficulties in remembering some of the formulas, sir.
You don't remember any formula except, for example, this is very simple. For example, if you have to, you may be thinking that, for example, this formula, you don't need to remember. I don't expect you to remember. This is something that I can give you.
So, sir, in midterm and exams, like
Yeah. This thing I can give you, but not this fellow.
okay, yeah, got it.
That I cannot give you, and this I cannot give you. These are all conceptual, right? Because if you understand the concept, this is easy to write down. You can derive, but this requires a lot of time. So I don't expect you to remember this formula, for example. Okay.
Okay, sir.
So, for example, this formula, I don't expect you to remember. You can ask me in the exam if I did not give. Otherwise, I would have given normally.
Okay.
So, for example, sigma y, this is the yield strength, this is the formula for sigma 1 plus, like this. Yeah.
Okay.
These formulas I can give you. That's not an issue.
Okay. Sir, November 8th is the midterm, right, sir?
November 8th is what day?
Saturday.
Saturday. So, what this is online exam or what is the plan?
Sir, online only, sir. This is online only, sir.
Online means you will sit in front
Midterm
of
will
the
be
computer
online.
and our code office will do the
Proctoring, sir.
proctoring. Correct?
Yes, sir.
Correct,
Okay.
sir.
Yeah. All right. So
Sir,
then we will have it on November 8th this exam, and so far what we have done is distortion. Until now we have done failure theories for ductile materials. In the tomorrow's class we will talk about failure theory for brittle materials, and that tomorrow most likely we will finish failure theories and also the effect of notches. Okay, and then and probably next class next week we will start talking about fatigue, but that I will not have it in the exam. I will only have until static failure theories for the exam. Okay.
Okay. Sorry. Hello, sir.
Yeah.
Any problem assignments you will give, sir, for our practice?
I will give you by one more assignment. I will give you by tomorrow evening. Okay.
Okay.
So that you can practice the static failure theories.
Right.
Yes, sir.
Thank you, sir.
Okay.
Thank you very
Any
much.
other questions?
What will be the pattern of exam, sir?
I don't know. I have not prepared the question paper.
But you have to.
Objective, descriptive, problematic.
It will not be objective. It will be descriptive. You have to solve.
Yes, sir. Yes, sir. Only thing, some difficult problem formulas we are expecting to provide you from your side, sir.
Don't remember any formula except the failure theory statements and their corresponding formula you should remember. But I don't expect you to remember equivalent stress formula and other things. Okay.
Right. Okay, sir.
And sir, there will be step marking problem. Like if I make a mistake in calculation, but conceptually, if the steps are right, there will be what I meant to say is
you will get marks.
Sure.
You will get marks. Not full marks. You will see it is like this. If you do a conceptual mistake, then there will be more cut in the marks. If it is a calculation mistake, although it cannot be forgiven, but in this class it can be, because now you are all practicing engineers. You cannot say that I have done a calculation mistake, isn't it? For our regular students, I understand, but for you, you know what is at stake when you are doing a calculation mistake, right? Things can blow up if you are not careful. So for you, for calculation mistake, there will be penalty. The penalty will be higher than what I would give regularly for my students in the class who are not practicing engineers. Yeah.
Right, sir.
Yeah. Any other questions?
Hello, sir.
Yes.
Maybe wrong question, but usually the mid semester and internal exams were conducted on Sundays.
Okay.
That gave us 1 day of advantage to revise and read more.
You want to do it on Sunday?
Yes, sir. November
would be nice,
9th.
1 minute. I have no problem. As long as our code office has no problem.
Then we'd like to request on Sunday,
Yes, sir.
Okay, 1 minute. They have said midterm 8th November, slot A, 3rd November. Question paper to be sent to code office by, why should we send the question paper to code office by 3rd? Okay, I will talk to them. Calculators are allowed. Okay. And it will be online proctored exam. And I will ask them if it can be done on Sunday. Okay. 8th November is a Saturday, no?
Yes, sir. Saturday.
Yes, sir.
Okay.
Sir,
I will
actually-
check with them. Yeah.
Sir, we have planned all the travels and all the things accordingly, 8th and 16th. So now
Where
if
are
we
you
are changing
traveling
all
to?
our plans. Sir, I'm traveling to Pune, sir. Pune and Mumbai.
Same here, Professor.
Okay. So you are thinking that it will be on Sunday. So you have, but this date is announced long back, no?
That's what, sir. 8th and 16th was announced. So that's why we have planned the accordingly. So now if we are changing, all our plans will get affected.
No, then I will not change. So since because others have made the plans, I thought everyone is asking. So let us stick to 8th to avoid any problems. Okay.
Okay, sir. Okay.
Thank you, Professor.
Okay.
Okay, sir.
Thank you. Bye.
Bye, sir. Thank
Yeah.
you.
Thank you, sir.
Thank you. Bye.